Right, so we're going to look at some of the problems from previous final exams. Right, remember that on Friday between 1 and 3, that is the time that your midterm will open in my e-learning. So it's already there, but you can't access it as yet. So during that time, you will go in there and you will attempt the midterm. You will have 2 hours to finish and submit it, right? And when you submit it at the end of the period, it would grade you. And then after that is only to do your final exam, which I believe is on the 18th. Okay, so without any further ado, let me put up the right. So we're looking at this. Right. So this was June 2020, right? So these are the instructions here, right? So we're actually looking at the problem here, right? So this is consider the identity, right? Well, let me focus more on the latter questions because I'll come back to question 1 and 2 and 3 because we did that earlier. So I'm looking more at the latter questions here. So I'll do it in somewhat of a reverse order because this is the more recent work we did. Right, so question 5, a system is modeled by the differential equation y triple prime t plus 4 y double prime t plus 6y prime t plus 4yt is equal to u double prime t plus 2u prime t plus ut, where ut and yt are respectively the input and the output of the system. Find the transfer function of the system. Okay, so remember when you're finding the transfer function of the system, right? You're taking the Laplace transform of the entire equation, but you're taking into consideration that the initial conditions are all 0. So which means if your initial conditions are all 0, the Laplace transform of just the first term will survive. So the Laplace transform of y triple prime t is s to the power 3ys, because all the other terms after that will have the initial conditions in them. So those terms will be 0, so they'll automatically vanish, right? And then the Laplace transform of 4 y double prime t is 4 s to the power 2ys, and all the rest of terms will vanish. And then the Laplace transform of 6 y prime t is 6 sys, and the Laplace transform of 4yt is 4ys. And likewise on the right hand side, the Laplace transform of u double prime t will be s squared us. And then for the other term here, the Laplace transform of 2 u prime t is 2s us, and then for ut will be us. So therefore, look at the terms here on the left hand side. So what we could do, we could just factor out the ys. You have s cubed plus 4s squared plus 6s plus 4 ys on the outside, and then on the right hand side it will be same thing. You factor out the ys, the us rather. You'll get s squared plus 2s plus 1. And then the transfer function hs is ys over us. Because remember, ys is your will stem from the output, and us will stem from the input. So it's the output over the input. So that will give you, if you pull this on the left here, then you'll have to take this on the right and it will come underneath. So you'll have s squared plus 2s plus 1 over s cubed plus 4s squared plus 6s plus 4. So that is the answer here for part A, right? Now determine the poles and zeros of HS, right? And they give you a hint here. S is equal to -2 is our pole. So that means S plus 1 is a factor. Sorry, S plus 2 is a factor, right? So the poles would be the zeros in the denominator, right? And the zeros will be the zeros in the numerator, right? So if you look at this here, this is a polynomial. You could treat it as a polynomial at third degree. And you know that S plus 2 is already a factor. So if you divide this by S plus 2, right, then you could get your remaining factors, right? Right, so I don't really have space here to do it. So I'm going to pull up the solution now and show you. Right? Yeah, look at here. Right? So if you go and you divide the other term, the S cube and so on, plus 4S squared plus 6S plus 4, you divide that by S plus 2, you'll end up getting S squared plus 2S plus 2. So these will be your two factors in your denominator. And then the S squared plus 2S plus 2 could be written as S plus 1 squared plus 1, right? And then, well, you could completely square here, right? So S plus 1 squared is minus 1. And then S plus 1 will be plus or minus G, right? Because it's square root of minus 1. So S will be minus 1 plus or minus G. So therefore, your other two roots will come from S plus 1 plus G and S plus 1 minus G. So which means your poles will be, right? Your poles will be S is equal to minus 2 and S is equal to minus 1 plus or minus G. So you have three poles, three simple poles, right? And the poles are the zeros in the denominator. And then in your numerator now you could factorize this as S plus 1 squared. So that will give you minus 1 to be a 0 of order 2. So you see your system has a 0 of order 2 at S equal minus 1. And then the third part of the question is you have to plot it on the S plane, right? So when you're doing your S plane, make sure you do your real axis, real S, your imaginary axis here, IMS, right? And you put a few points here in order to locate your poles and your zeros, right? And remember, you have a 0 at minus 1, so you put a little circle here. When you're doing this, it's always good to have a legend here. X is our pole. So when you're doing yours, make sure you have a legend, right? I mean, it's standard that you have an X for a pool and a 0 for 0, but just to make sure that people don't mix it up, it's always good to have a legend, right? And then you could put like the S plane here. Right, so make sure all that in your plot, right? So this is your one of your poles here. You see, I have an X, another X at the bottom, and another X here. So this here will be 1 plus G. And this is minus 1 plus G. Okay, you're on minus 1 down here. And this is, sorry, minus 1 minus G. So let me fix this here. This should rather be G. And this should be minus G. Right? So therefore here will be minus 1 minus G. And here on top here will be minus 1 plus G. So those are the positions of your poles, and then you have a pole at minus 2. So that pole line on the real axis. And then you have a 0 here, right? And the 0 here is at -1 on the real axis, and the little 2 on top indicating that is a 0 of order 2. Right. So that is the third part here of the question. Right. The impulse response HT of the system may be obtained by taking the inverse Laplace transform of the transfer function. So you want to take the inverse Laplace transform and you want to determine HT. Right? So let's go back here now to the right. So we have s squared plus 2s plus 1 over s plus 2 into s squared plus 2s plus 2. And then you could break up this into partial fractions, right? This is a simple factor, s plus 2, a over s plus 2. And then you're adding b over a quadratic, irreducible quadratic factor. So you have bs plus c over s squared plus 2s plus 2. And if you multiply it throughout, you'll get a into s squared plus 2s plus 2, and you'll get bs plus c into s plus 2. And then if you multiply everything on the right-hand side and you equate coefficients, so you group all the terms in s squared, you'll get a plus bs squared, 2a plus 2b plus cs, and then 2a plus 2c. So this is your constant here. So from that now, your coefficient are s squared, a plus b, so the coefficient here is 1. So a plus b is 1. Then 2a plus 2b plus c would be 2. You see that here? And finally, 2a plus 2c would be equal to 1, right? Okay, and when you solve this here, right? So this is a system of 3 equations here in 3 unknowns basically. You'll get a is equal to a half, b is a half, and c is 0. So c is 0 here. So a is a half. So that is the Laplace transform of a half over s plus 2 plus a half s over s plus 1 squared plus 1. Right? So we write this here as s plus 1 squared. And then you're taking the Laplace inverse of 1 half over s plus 2. That is a half e to the minus 2t. And then this here could be broken as a half s plus 1 over s plus 1 squared plus 1 minus a half one over s plus 1 squared and why we write it like this is for in order to apply the shift property. So you have a half s plus 1 over s plus 1 squared plus 1. So if you shift this here by minus 1 here, you'll get s over s squared plus 1, and you know that the Laplace inverse of that is cos t, right? So your Laplace inverse of all of this here for this part here will be a half e to the minus t, which is the shift, the minus 1, and the Laplace inverse of 1 s over s squared plus 1, which is cos t. And then the next part here will be a half e to the minus t, which same shift again, minus 1, but this would be the Laplace inverse of 1 over s squared plus 1, which is sine t. So hence the result here, right? Any questions on that so far? Okay. All right. So what I'm trying to do here, on the paper itself, I'll mark certain things, but when the solution kind of involved, I'll have to go to the solution sheet to show you it then, because it will take too long to write it out on the question sheet itself, right? So that takes care of question 5. Now look at question 6. So you have a transfer function again here, and let GT be the Laplace inverse of GS, right? Use the initial value theorem to determine G0 plus, which is the limit of T approaching 0 from the right GT, right? Because you remember using the initial value theorem, right? The theory of the initial value theorem is that the limit, this is what we did last day, of T approaching 0, GT, is actually equal to the limit. So you don't really have to find the benefit with this here is you don't have to find the inverse transform, right? You could just take the limit here of S approaching infinity, SGS. Which is this here with S. So if you write that there now, you'll get minus 2 S squared, because you have to multiply by S on top here, right? And then you'll get what again? You'll get minus 14S. And you divide by S squared minus 2S plus 10. So this is your SGS, and then you take the limit here as S approaching infinity. Now, when the limit of the variable S approaches infinity here, what you have to do? Remember, you have to divide the entire rational expression here by the highest power S in the denominator. And what is the highest power S in the denominator? S squared. So every term have to divide by S squared. So if you do that, what will happen? You'll get minus 2, because you're dividing this by S squared, minus 14 over S. And then in the denominator here, you'll get 1, right? Minus 2 over S. Plus 10 over S squared. Right? And I need to write the limit here. S approaching infinity. So you know these terms here, once you have S in the denominator of any term, that this will approach 0, this will approach 0, and that will approach 0. So you'll get minus 2 over 1. So the limit of S approaching infinity is minus 2. So that is this part here, right? Does the final value exist, right? So now in order for the final value, for the limit to exist as T approach infinity, GT, right? What condition must be satisfied? Remember, think about the poles. The poles must lie in the left-hand plane, right? Of the S plane. So if you look at this here, the denominator here, let's see if we factorize the denominator here and we check out the poles, right? So this will be S minus What factors will give you 10? You'll get 5 and 2, 10 and 1, right? And when you cross multiply, minus 5 plus 2 is minus 3. 5 minus 2 is 3. So you can't factorize this like that. So this will most likely you had a completely squared here, right? So you have, right? So let me just pull it up here to make it easier for us, you know, right? Right, so look at it here. So the first part here was minus 2, that is your initial value theorem. So G naught is minus 2, which we already did, right? And then the other part here now, part B, right? You're taking GS here. Guys, S plus 7 over S minus 1 squared plus 9, right? Because if you factorize this first part here, you'll get S plus S minus 1 plus 1, and then you add 9 here. So therefore, you will get in the denominator here, your poles here will be 1 plus 3i, sorry, 1 plus 3j and 1 minus 3j, right? So if you look at that here, what's going on here? And GS has poles lying strictly on the right-hand side of the complex plane, because 1 plus 3j is here and 1 minus 3j is at the bottom here. And we know from the theory, right, that if that is the case, then the limit at t approaching infinity, gt, does not exist, right? So you could do something like this here, find the poles, right, factorize the denominator, and then realize that the poles not lying in the right, they're not lying in the left-hand plane, they're lying strictly in the right-hand plane. So therefore, you could, if you need to do it, you could draw a little plot and show that, and then you could give a brief explanation, and then say that the limit at t approaching infinity gt wouldn't exist. Now, if the poles lie on the left-hand plane, or even if they lie on the imaginary axis, the limit would exist, right? Because therefore, you will still have some level of stability, right? Once it's marginally stable or it's stable, the limit would exist. If it's unstable, that is the only condition where the limit would not exist, right? So that is important. Right, so look, that part there was the other 3 marks. All right, the following function is a periodic function, and the period here is pi, right? So you have here sine 2t, t between 0 and pi over 2, and then 0 for t between pi over 2 and pi. Sketch the graph for at least 2 periods, right? So between 0 and pi over 2, this is your graph here, sine 2t, right? Between pi over 2 and pi, 0 is defined to be 0. And then, so that will be 1 period. From here to here is 1 period, right? So all you do now is you repeat that period. So you go up again between pi and 3 over 2 pi, sine 2t, and then from 3 over 2 pi to 2 pi, the graph is 0. So that will be 2 periods. So at least 2 periods. So we just put in an extra period here again. Make sure your labeling is on par. So 3 over 2 pi, 2 pi, then 2 pi and 2.5 pi, and then the other point here will be 3 pi, right? Right. So now you want to find the Laplace, right? So that is 2 marks. Determine the Laplace of xt. So what you have to do here, you have to write the function, right, in terms of the Heaviside function. right? So you have L 1 minus h t minus pi over 2 by sine 2t. You're taking the Laplace of that and you're dividing. Remember, when you're finding the Laplace of a periodic function, you're always dividing by 1 minus e to the minus s by your period. Right, so let me go back here and show you that. Right, so your period here is pi. So when you're finding the Laplace of any periodic function, remember you have to always divide by 1 minus e to the minus s t, and t is your period, and your period here is pi. So therefore your t would be replaced by pi. And then if you write this in terms of Heaviside function, right, this will be 1 minus h. The two endpoint here is, one endpoint is 0 and the next endpoint is pi over 2. So that is h t, which is 1. So that is 1 here, and then h t minus pi over 2. And then you have to multiply this by sine 2t. Right, so we sine 2t here by the 1 and then sine 2t by the Heaviside t minus pi over 2. But anytime you have a Heaviside, in order for it to match up with that function, the function must be of this form here, t minus pi over 2. So therefore you have to make an adjustment here then. Right, so look at here. The Laplace of 1 minus h t minus pi over 2 by sine 2t. So of course here when you multiply the sine 2t by 1, you'll get sine 2t, and then sine 2t by t minus pi over 2. Right, so now the 2t had to be of the form t minus pi over 2. So you have h at t minus pi over 2 sine 2t minus pi over 2. Right? Now, so you're using your trig identity here. Right, this will be sine 2t cos 2 pi over 2. And then you're minusing cos 2t sine 2 pi over 2. Right? So now we know that sine 2 pi over 2 will be just sine pi, which is 0. So this term here will drop off. Right? Sine 2t cos pi over 2, well, that will be cos pi. Right? So that will actually be minus, cos pi is minus 1. So that is minus sine 2t. Right? So therefore, right? So if minus sine 2t is sine 2 into t minus pi over 2, then sine 2t will be minus sine 2 into t minus pi over 2. So therefore, if we replacing this here by a minus of this, so a minus and a minus will give us a plus here, right? That is why the sign here change in front. And now this is of the form, the heavy side is of the form, t minus pi over 2 sine 2 into t minus pi over 2, which is of the same form here, for it to match up. And then you're dividing it by 1 minus e to the minus s over pi, because pi is your period. And the Laplace 2t is this here, right? So the Laplace sine 2t is 2 over s squared plus 4. And the Laplace h t minus pi over 2 sine 2 into t minus pi over 2 will be e to the minus s pi over 2, 2 over s squared plus 4, right? And that could be written in this form here, 1 plus e minus s pi over 2 into 2 over s squared plus 4. Because you'll get back this term here, the 2 over s squared plus 4, and you'll get back the next term with the e to the minus s over pi, sorry, e to the minus s pi over 2 by 2. So this here is exactly what we have on top here. And then the bottom here, right? You could treat this as the difference of 2 squares. So you'll have 1 plus e to the minus s pi over 2 into 1 minus e to the minus s pi over 2. And then these two will cancel and you'll end up with 2 over s squared plus 4 into 1 over 1 minus e to the minus s pi over 2. So these are the little tricks here you have to learn to be able to see and work out when you're doing problems of this nature. Right? So you have to look at it carefully. So I'll go back to the paper here now. Right? So question 1. Consider the identity sine omega t is equal to e to the j omega t minus e to the minus j omega t over 2j. Use the above identity and the linearity property of the Laplace transform to show that the Laplace sine omega t is omega over s squared plus omega squared. Right, so this basically straightforward. You could get this directly from your notes, right? And if, right. So what we do here, we just treat this, the Laplace sine omega t is 1 over 2j into 1 over s minus j omega minus 1 over s plus j omega. Right, so if you look at it carefully, it's basically you're taking the Laplace of all that. And by definition, this will be 1 over s minus j omega. And this part here will be 1 over s plus j omega. And then you have a minus on inside here, and then you pull your 1 over 2j on the outside. Right? So that is it here. And then the LCM here will be s squared plus omega squared. Right? So then you got to cross multiply here by s plus j omega, and then you got to cross multiply on this side. And then s minus j omega. And notice here s plus j omega, so the s will cancel each other. And then you'll end up getting j omega plus j omega. So that will be a 2j omega. And then the 2j's will cancel here, so you'll just get omega over s squared plus omega squared. And the radius of convergence here is the real axis must be great, real s must be greater than 0. right? They ask that here. Justify your answer. Sketch the region of convergence in the complex S-plane. Right? So recall that e to the omega t is 1 over s minus omega when the real s is greater than real omega by linearity. The radius of convergence of this here will be 1 over 2j, the Laplace transform e into e to the j omega t plus the Laplace transform e to the minus j omega t. So the real s must be greater than the max of these two terms here, which is equal to 0. So this is your region of convergence here. So real s must be greater than 0. Let a be a non-zero real constant. Determine the Laplace inverse of s squared plus as over s cubed minus a s squared plus a squared s minus a cubed. Use the definition of Laplace transform to determine the Laplace t e to the t. And what is the region of convergence? Right, so this is the problem here. So this is your s squared plus as over s squared plus a squared into s minus a. This bottom part here could be factorized into this here. So you end up getting, using partial fraction, as plus b over s squared plus a squared plus c over s minus a. And then you multiply it throughout by s squared plus a squared s minus a, and you'll get as plus b into s minus a plus c into s squared plus a squared. And then if you equate coefficients here, you'll get a plus c is 1, b minus a by large A is equal to a, and then a squared c minus ab is equal to 0. So therefore, the second equation leads to ab minus a squared a is equal to a squared. And then if you substitute 3 into 4, right, you'll get c minus a is equal to 1. Which with 1 implies that c is equal to 1, a will be equal to 0. Because if c is 1, then a plus 1 is equal to 1. A ought to be 0, obviously. And b will be equal to a. So therefore, if a is 0, b is equal to a. So you have a over s squared plus a squared. And c is 1 over s minus a. So if you take a Laplace inverse of this, this will be sine at, and this will be plus e to the at. The second part, now you're using the definition of the Laplace transform to find the Laplace inverse of t e to the t. So that's the integral between infinity and 0, e to the minus st, t e to the t dt. So we could use our lower exponents here to combine the minus st and the e to the t. So you get minus e to the minus s minus 1 t by t. And then here now, you take the limit as r approaches infinity. The integral between r and 0, e to the minus, open bracket, s minus 1 t dt. So you use your integration by parts. Let v equal t. And du is minus, open bracket, s minus 1 t. So therefore dv will be dt. And u will be e to the minus, open bracket, s minus 1 t over s minus 1. But this is negative s minus 1. So you have a negative on the outside. So uv will be t e to the minus te to the minus, open bracket, s minus 1 t over s minus 1. And then u dv will be minus, which is plus, e to the minus, open bracket, s minus 1 t over s minus 1 dt. So the right hand side now you have to integrate it with respect to t, right? So now when you integrate this a second time, you'll get s minus 1 squared in the denominator, and you'll get negative because it'll be a negative e to the minus, open bracket, s minus 1 t. And you're taking the limit here as r and 0. So the first part here, this will be r, and you have e to the minus s minus 1 in bracket by r over s minus 1. And then if you put 0 here, of course the next term will be 0. So that won't survive. Now you're looking at this term here. So you put in r here, it'll be negative, so you put that on the right. And then you put in 0 here, that will be 1 over s minus 1 squared, right? So these two terms here, when r approaching infinity, this here will approach 0 and this here will also approach 0. Although r approaching infinity here, in the exponential position, it will reach infinity a lot faster, so this value will approach 0. So all you'll have surviving is the middle term, 1 over s minus 1 squared. And it means that real s had to be greater than 1. So the radius of convergence here must be greater than 1. Right? So look at that carefully. So let's look at this question now. Consider the following piecewise defined function. So ft is 0 between 0 and pi, is sine t between pi and 2 pi, and is t minus 2 pi between 2 pi and infinity. Express ft in terms of Heaviside functions and determine the Laplace, right? So this part here won't give us any contribution. So this part here, the second part and the third part is where we get any contributions from. So you have the second part, the function is defined to be sine t, and the two endpoints are pi and 2 pi. So you'll have the Heaviside t minus pi, the left endpoint, minus the Heaviside t minus 2 pi, the right endpoint, multiplied by sine t. And then in the next instant, the function is defined to be t minus 2 pi. So you have the Heaviside t minus 2 pi, that is the left endpoint, and the right endpoint infinity, so that won't give us any contribution. So this is just straightforward t minus 2 pi by Heaviside at t minus 2 pi by the function t minus 2 pi, which is already in the form that it needs to be in. So we don't have to do no adjustment with this second part here. The second part here is easy to evaluate now, right? So now I need to multiply this here, right? So I just wrote here sine t minus pi will be sine t cos pi. I did something similar to this a while ago using trigonometric identities. Minus cos t sine pi, which is minus sine t. So it means that sine t will be minus sine t minus pi. So this term here, when I multiply it by this here, I'll get sine t minus pi. I make the adjustment, and then the negative goes in front here. Minus h t minus 2 pi sine t minus 2 pi, and then plus h t minus 2 pi t minus 2 pi. The second one here will work out when you put the t minus pi, 2 pi in it. So this one will remain as sine t. So this is supposed to work out to sine t, right? So that is sine t cos 2 pi minus cos t sine 2 pi. Any multiplier sine pi is 0. So this term is 0. Cos 2 pi is 1. So you just get sine t. So your sine t by this second term here will be negative h t minus 2 pi sine t minus 2 pi. So you can replace the sine t by the t minus 2 pi, so it will be in the form. And then the Laplace here of h t minus pi sine t minus pi is just negative in front, e to the minus s pi over s squared plus 1. And then this one here is the same thing, minus e to the minus 2s pi, because 2 pi here is your t naught, over s squared plus 1. And finally, this is the Laplace h t minus 2 pi t minus 2 pi will be e to the minus 2s pi. And we know that the Laplace t is s squared. So 1 over s squared. So you're dividing by s squared. Right? So that's question 3. Question 4 now. Solve the initial value problem. Right? So you take your y, your Laplace transform y double prime. You take your Laplace 4yt, and then you take your Laplace ft. But remember, ft is piecewise defined, right? It's defined to be 40 between 0 and 1, and 4 between 1 and infinity, right? So now let's look at that here. To avoid the right. So in the first instance here, the piecewise function, you're taking the two endpoints will be 0 and 1. So 1 minus the heavy side at t minus 1 by 40. And then the other one, the left endpoint is 1. So h at t minus 1 by 4. Right? So you have, when you multiply 40 by this here, you get Laplace of 40. And then this one here, this could be expanded as minus 4t h That is this term here when you multiply by the 40. So things like this will keep coming up a lot. Yeah, minus 4. H t minus 1 t minus 1. Because the function ought to be at the same form, t minus 1. And then you're adding 1 here. So this here will be really this here. Minus 4 into h t minus 1 t minus 1 plus h t minus 1. Right? So what you will happen here? You'll get minus 4 h t minus 1 t minus 1, which is essentially this term here. And then you'll get minus 4 h t minus 1, and then you have a h t minus 1 by plus 4. So that will cancel. So therefore, you'll just get the Laplace of 4t minus the Laplace of ht minus 1, 4t minus 1. And the Laplace inverse of this, sorry, the Laplace of t here is 1 over s squared. So you'll get 4 over s squared. And then here now the Laplace will be minus 4 e to the minus s over s squared. Taking the Laplace transform on both sides of the differential equation now. So you want to take the Laplace transform here. You'll get s squared ys plus, sorry, minus sy naught minus y prime naught plus 4 ys is equal to, well, we already worked out this part here already, right? We already found the Laplace of ft. So the left hand side here will be y naught is 1 and y prime naught is 0. So this term will vanish. So you'll get s squared plus 4 ys, and then you're carrying the minus s because it's minus s by 1, so that will be plus s here. And then the other terms that we got from 4 over s squared minus right, let me just check this. Right, so this is what you'll end up with here. So therefore ys, you'll have to divide through the right hand side by s squared plus 4. So you'll get s over s squared plus 4. You'll get 4 over s squared into s squared plus 4, and you'll get minus 4 e to the minus s over s squared into s squared plus 4. So let's look at it here. You see it here? So this first term here, we could find the Laplace inverse of this This is straightforward. But this term here and this term here, both will have to be broken into partial fractions. So let's deal with this one here, because whatever we get for this one, it will apply to this one as well, because they have the same denominator, right? So you have 4 over s squared into s squared plus, well, using our substitution here, u equal s squared. A over u plus b over u plus 4. So you have 4 here will be equal to a into u plus 4 plus b into u. And then when you're solving this here, right? It's easy to solve. You just put u equal minus 4 and you'll get b to be minus 1. And if you put u equals 0, you'll get a to be 1. Right, so you have here 1 and minus 1. So you have s over s squared plus 4 plus 1 over s squared minus 1 over s squared plus 4. And then you have your e to the minus s. So you pull your e to the minus s on the outside, and then you have the same partial fractions as this here, 1 over s squared minus 1 over s squared plus 4. And then the next step now is just to take the Laplace inverse. So you have the Laplace inverse here, cos 2t. The Laplace inverse of 1 over s squared is t. The Laplace inverse of 1 over s squared plus 4 is a half sine 2t, because you have a 2 on top here, and you have to put a 1 over 2 on the outside to cancel the 2. And then here now, this will be heavy side. Minus h t minus 1 into t minus 1 here, minus a half sine 2 into t minus 1. Right? Now the reason why we didn't include the 4, because remember you use the substitution, s squared is equal to u, right? So 4 yeah, the fact that the s squared is equal to u, and replace the s squared by u, right? Therefore we get the square root of u equal to 2. So that is why here we did not consider the 4 here, because we compensated for it already in the substitution, right? Okay, so right, so that takes care of this paper. So this was a pretty long paper, right? This was from 2020. Normally your paper wouldn't be this long, so that is why I went through this one here. So now I want to look at another one, right? So I look at the 2019 now. Hopefully the 2019 won't take as long. Let's see the 2019. Right. Right. Consider the following piecewise defined function. So the function here is 0 between 0 and 1, is 1 between 1 and 2, and it's 0 between 2 and infinity. So the only part here that will really give us a contribution is when the function is defined to be 1. The 2 endpoints here, so that will be the heavy side at t minus 1 minus the heavy side at t minus 2 by 1. So if you're taking the Laplace of that, you'll get e to the minus s over s, because the Laplace of ht minus 1 and the Laplace of minus ht minus 2 will be e to the minus 2s over s. So that is the first part there. State the region of convergence. Now, since you're dividing by s, right, the entire s plane, because s equals 0 is a removable singularity, so which means the region is the entire s plane. So that was question 1. Pretty straightforward. Consider the following initial value problem. Y double prime t plus 2y prime t plus 2it is the heavy side at t minus pi minus the heavy side at t minus 2 pi. And you have your initial conditions here, y naught is 0 and y prime naught is 1. So look at I did it here. I took the Laplace throughout. So you want to take the Laplace of the differential equation and you want to show it equal to this. So this is a nice question here. When they're telling you exactly what they want you to show it equal to, that is a nice kind of guide. So you know exactly what your solution has to end up looking like, right? So look at taking it here now. S squared ys minus sy naught minus y prime naught plus 2sys minus 2y naught plus 2ys, and the Laplace of the heavy side t minus pi will be e to the minus pi s over s, and then the other one here will be minus e to the minus 2 pi s over s. And then we collect all the terms in s ys here, so that will be s squared plus 2s plus 2. And then this here, this term will vanish because y naught is 0. This will be minus 1, and this one will vanish as well, 2y naught. So the minus 1 you carry it on the other side of the equation, so you get 1 plus e to the minus pi s minus e to the minus 2 pi s all over s. And then you have to divide throughout on the left hand, on the right hand side now by s squared plus 2s plus 2. So that you'll get 1 over s squared plus 2s plus 2, and you'll get e to the minus pi s minus e to the minus 2 pi s over s into s squared plus 2s plus 2. So you see how you end up getting it there? So these are the steps here that allowed us to arrive at ys being this answer here, which was given. But we had to show it, right? And now we had to take the Laplace inverse now and find yt, right? So that part there will be a little involved. So I might need to pull up the page with that one in order to show you it, right? So just give me a few seconds here. Right, so this is the working here that showing us the second part, right? So you want to find the this part here, right? So you're taking 1 over s into s squared plus 2s plus 2, and you're breaking it up into partial fractions, right? And then you're going to multiply it by e to the minus pi s minus e to the minus 2 pi s in order to arrive at your final answer. So this is a irreducible quadratic fraction, so a over s plus bs plus c over s squared plus 2s plus 2. And then if you multiply throughout by s squared plus 2s plus 2, you'll get a into s squared plus 2s plus 2 plus bs plus c by s. and then your group terms are according to coefficient a plus bs squared, 2a plus cs, and 2a. So which means a plus b will be equal to 0. 2a plus c is 0, and 2a will be 1. So if 2a is 1, a is a half, right? So if a is a half, a plus b is 0. So b had to be minus a half. And then if 2a plus c is 0 and a is a half, c had to be minus 1. So you're taking the Laplace inverse of 1 over s plus 1 squared plus 1. This was the first irreducible quadratic factor here. You write it like this in order to use the shift property. And then the next one was e to the minus pi s minus e to the minus 2 pi s. Remember, your a is a half, your b is minus a half, and your c is 1. Sorry, your b is minus a half, and your c is minus 1. So minus of all this will give you your minus 1 back. So you have 1 over s plus 1 squared plus 1 into plus e to the minus pi s minus e to the minus 2 pi s into a half over s minus a half into s plus 1 plus 1. And if you take the inverse here, you get e to the minus t, because the shift here is minus 1. And then you take the Laplace inverse of s squared, 1 over s squared plus 1, which is sine t. And these will be the same thing involving the heavy side. So this will be the heavy side at t minus pi, a half, because it minus pi s over s, the heavy side. The Laplace inverse of that is the heavy side at t minus pi by a half. And then the next one will be minus a half e to the minus t minus pi, pi in bracket cos t minus pi, because this is minus 1 again, but this is s. So s over s squared plus 1 cos, the Laplace inverse of that will be cos. And we know that if you have a heavy side involved and your t naught is minus pi, it will be t minus your t naught. And then the next one will be 1 over s squared, s plus 1 squared plus 1, which again is using your shift is minus 1. And that is the Laplace inverse of 1 over s squared plus 1, which is sine. And you're using your heavy side here, your t naught here, t minus pi. And then, so this will give me 1, 2, 3, 4 terms, right? So that is how we'll get all these terms here. Right, so it's a little involved, so look at it carefully there. Right. So I'm back now on the paper here. Oh no, I'm not on the right paper. Right. So that is why it's so many marks, because it's a little involved. A system is modeled by the differential equation y double prime t plus 3y prime t plus 2yt is equal to u prime t minus ut. And you know that ut would be your input, right? And yt is your output. So you wanted to find the transfer function, right? So you know your transfer function is your ys over your us. So you'll end up getting s minus 1 over s squared plus 3s plus 2. Because you just have to take the Laplace transform throughout, and just the first term will survive because all your initial conditions will be 0. So when you go through the process there and you find HS, you'll get s minus 1 over. You have a fast way to do this, you know, just like a mechanical way of doing this. What is the Laplace here? This will be just s, and this will be minus 1. This here is what? S squared, because it have a double prime in it. This is a 3s here, and this here is that's a 2 because it has no prime in it. So it's just a matter of dividing the right hand side by the left hand side, and that's how you get this here. That's just like a mechanical way of doing it, but in the previous paper I showed you the correct conceptual way of doing it. I know the mechanical way could always help you to arrive at the answer quickly then, right? So now you see I factorize the denominator here, so I could see my poles, right? So here now they want us to find the impulse response by taking the inverse of this here, right? So of course, if we take the inverse of this, that would be s minus 1 over s plus 1 into s plus 2. And you break it up into partial fractions. A over s plus 1 plus b over s plus 2. And then down here, you multiply throughout by s plus 1, s plus 2. So you get s plus 1 is a into s plus 2 by plus b into s plus 1, right? And from this here, if you put s equal to minus 2, you'll get minus b is minus 3, so b is 3. And if you put s equal to minus 1, you'll get minus 3a. Is minus 2. So a is 2/3, right? So it's just to take the Laplace inverse 2/3 1 over s plus 1 plus 3, the Laplace inverse 1 over s plus 2, which is 2/3 e to the minus t plus 3 e to the minus 2t. Consider the following transfer function. GS is s squared plus 2s plus 4 over s cubed plus 3s squared plus 2s. And we have to use the initial value theorem to determine the limit at t approaching 0 of gt, which is just the limit at s approaching infinity, sgs, right? So it means that you'll have to multiply this here by s. So you'll get s cubed plus 2s squared plus 4s over s cubed plus 3s squared plus 2s. And you divide by the highest power in the denominator, which is s cubed. So this first term and this first term in the numerator and the denominator will be 1. And the second term, right, will be 2 over s plus 4 over s squared. And then in the denominator will be 3 over s plus 2 over s squared. So anything with s in the denominator will approach 0. So you'll just get 1 over 1, which is 1. So the answer is 1. So I just fast track it here and put 1 as the answer, but then you show the working in your solution. Right? Any questions on that so far? I kind of going a little fast because I want to try and get through another one here before we finish. I hope you're following carefully because I mean it's the same thing you're going to be doing in your exam. Use the final value theorem to determine the limit at t approaching infinity, gt. So that is the same as the limit at s approaching 0 now, using the final value theorem, SGS, right? Now, When you use any final value theorem, although you're multiplying by the S, instead of multiplying it at the top, right? What you do here, if you're multiplying by S here, when you use any final value theorem, since you're taking the limit at S approaching 0 this time, you cancel S in each term in the denominator. So this S will cancel with one S here, it will cancel with another S here, and will cancel with another S here. So you'll end up getting S squared plus 3S plus 2. And then in the numerator, you'll have the same thing, S squared plus 2S plus 4, because remember you're not multiplying it by the terms in the numerator, you're canceling it with each term in the denominator. So if S approaching 0 here, what will happen here? This could be 0, this could be first and second term numerator and denominator will be 0. And you'll just get 4 over 2, which is equal to 2. All right? And then the third part of this, the fifth question in this paper, you know, the following function is periodic. The function is t, and it's periodic with period 2. Xt plus 2 is equal to xt. So the period is 2 then. Sketch a graph of xt for at least 2 periods. So between 0 and 2, the graph is 2. Sorry, it's t. So t will be like a straight line here, right? When the t-axis is 2, the xt axis will be also 2. So your gradient here is 1, right? So this is 1 period, then you start at 2, and you go to 4, another period. You start at 4, you go to 6, another period. So I actually draw 3 periods there, because they say at least 2. And now you want the Laplace transform. So the Laplace transform of a periodic function is the Laplace transform of the function divided by 1 minus e to the minus s by the period. And in this case here, your period is 2, so it's 1 minus e to the minus 2s. Right? Now remember, your Laplace, your function had to be written in terms of Heaviside functions. So between 0 and 2, right, that would be 1 minus h at t minus 2 by t. So that will give us the Laplace at t, and then minus h t minus 2 into t minus 2 minus 2 h at t minus 2, and you expand this here, because the minus t minus 2 could be written as minus ht minus 2 by t minus 2 minus 2ht minus 2. That's how you expand this here. We're doing that all the time. So if you take the Laplace at t, you get 1 over s squared. The Laplace of the Heaviside t minus 2 by t minus 2 is minus e to the minus 2s over s squared. And then the Laplace 2h at t minus 2 is 2 e to the minus 2s over s, all divided by 1 minus e to the minus 2s. So what I do here in the numerator, I make s squared my LCM. So which means this third term here I have to multiply by s. So I end up with 1 minus e to the minus 2s minus 2s e to the minus 2s over s squared into 1 minus e to the minus 2s. So that gives me the solution there, right? So look at it carefully once again. Right, this is 17. So let ft be a piecewise function, t between 0 and 1, 0 between 1 and infinity, Draw a clearly labeled sketch of ft. So look at here. So between 0 and 1, the function is t, and between 1 and infinity is 0. So it will continue along this axis here, right? If you want just for completeness, you can put t here, and this is your ft. Make sure you label your axes on them properly. Express ft in terms of Heaviside step functions. So here now, this is the only part here you're dealing with because this part is 0. 1 minus h at t minus 1 by t, which is, when expanded, could be t by 1, which is t, and t by h at t minus 1 is minus h at t minus 1 by t minus 1 minus h at t minus 1. Right? Using your answer from part B or otherwise, find the Laplace transform. Right? So the Laplace transform, this is fairly straightforward. Look it up here. So the Laplace transform t is 1 over s squared. The Laplace transform h t minus 1 is minus e to the minus s over s squared. And the Laplace transform h at t minus 1 is e to the minus s over s. And if I want here, I could just write s squared as my LCM. So I'll have to put on top here 1 minus e to the minus s minus s e to the minus s. And that completes it. Question 1. Consider the following initial value problem. So you have y double prime t plus 2y prime t plus 2yt is equal to the delta Dirac t minus pi. And you have y naught is 1 and y prime naught is 0. So I take my Laplace here, s squared ys minus sy naught minus y prime naught plus 2sys minus 2y naught plus 2ys, and the Laplace of the delta t minus pi will be just e to the minus s pi. So the y naught here is 1. So this term will be minus s. This term is 0. This will be minus 2. Right? So if you have minus s and minus 2, you could carry those two terms on the right hand side and you'll get s plus s and plus 2 plus e to the minus s pi. And then you factor out the ys here on the left. Right? So when you divide now, you'll get s plus 2 over s squared plus 2s plus 2 plus e to the minus pi s pi over s squared plus 2s plus 2. Right? And then here you could break up this into s plus 2 into s plus 1 plus 1. So that will be s plus 1 over s squared plus 2s plus 2, which could be factored into s plus 1 squared plus 1. And then you have 1 over the same thing, s plus 1 squared plus 1. And then you have the e to the minus s pi over s plus 1 squared plus 1. So from here, you could break it into this here. It's easy to see that. And now you want to determine your inverse transform, right, of the initial value problem. So for this here, remember you could use your shift property, minus 1. So you have e to the minus t. And then you'll have s over s squared plus 1, which is cos t. And this one goes, same thing, e to the minus t, but this is sine t because 1 over s squared plus 1 is sine t, the Laplace inverse of that. And this one will be the Heaviside at t minus pi, e to the t minus, because it's minus 1 again, so minus, but remember you can't just put minus 1, you have to put the value that you have here t minus pi because it had a match up with the heavy side. And then you have your sine here, t minus pi once again. So this is your Laplace inverse. Part 3, question 3 rather. So you have a transfer function there, s squared plus 2s plus 4 over s cubed plus 3s squared plus 2s. Right? So what I did, I pull out a s in the denominator. So I have s into s squared plus 3s plus 2. So this quadratic could further factorize into two simple factors. So they determine the poles and zeros. So you'll have a pole at s equals 0, s equal minus 1, and s equal minus 2. Right? And then in the numerator now, right? You want to find your zeros now. So you want to factorize this top part here. So that will be s plus 1 squared plus 3. So s plus 1 squared will be minus 3. So the square root of minus 3 is plus or minus 3i. So s here is minus 1 plus or minus 3i. Right? So your zeros, you have two zeros, complex zeros. Right? So look at sketch it here. I have x for pole, 0 for 0. You have the s plane, real s, imaginary s. You see how I have all my labels here? I have my poles here at 0, minus 1, minus 2, and I have my 0 here. This is minus 1 plus 3j, and this is minus 1 minus 3j. I have I here, but just standard. Sometimes they use I, sometimes they use j, right? So in this course here, we're using j as our complex unit. Anything on that so far? Any questions on that? No questions? Okay. Okay, now we have to use the initial value theorem to find the limit of ht as t approaches 0 from the right. Right? The plus mean from the right. So you have here the limit of t approaching 0 from the right, ht, will be the limit of s approaching infinity. So we don't have to find the inverse transform, s or hs, right? So what we do here, we multiply the top here by s. So you'll get s cubed plus 2s squared plus 4s. And you have in the denominator s cubed plus 3s squared plus 2s. And then you divide the numerator and the denominator by the highest power s in the denominator. So you'll end up with 1 plus 2 over s plus 4 over s squared divided by 1 plus 3 over s plus 2 over s squared. And these terms here will approach 0. So you'll get 1 over 1, which is 1. Right? And you want to use the final value theorem now. So you're taking the limit of t approaching infinity, ht. That is the limit of s approaching 0, shs, which is the same thing as this here. But this time, when you multiply this by s, you want to cancel s in each term in the denominator. So you'll end up with s squared plus 3s plus 2. And in the numerator, s squared plus 2s plus 4. And you know as s approaches 0, the first two terms, top and bottom, will approach 0. So you'll get 4 over 2, which is 2. Right? So we did one similar to that in the previous paper. Consider the periodic function. Ft is sine t, and you have your period here is pi, t between 0 and pi. Draw a clearly labeled sketch of Ft. right? So I draw my graph here. So this is my t-axis, this is my ft axis. So between 0 and pi, right, the function is defined to be sine t. Then, so that is one period. So then you do it again from pi to 2 pi, that is another period. And then from 2 pi to 3 pi is a third period. And now you want to find the Laplace transform. So you take the Laplace transform of the function and you divide it by 1 minus e to the minus s by the period, and the period here is pi. So remember you have to find the Laplace transform in terms of Heaviside function. So this will be 1 minus ht minus pi by sine t, right? Which is sine t by h at t minus pi. And we know that minus sine t is sine t minus pi, because you have to write the t here in terms of the Heaviside, t minus pi. So it means that sine t will be minus all right, so we cannot repeat this a lot. Right, so if you have the sine t here, you're replacing that by minus sine t minus pi. So if this is you remember that a minus, so the minus will convert into a plus here. So we take in the Laplace of sine t, which is 1 over s squared plus 1, and the Laplace of h at t minus pi sine t minus pi is e to the minus s pi 1 over s squared plus 1. And you're dividing that by 1 minus e to the minus s pi. So that will just give you 1 plus e to the minus s pi over s squared plus 1 into 1 minus e to the minus s pi. Right, so that takes care of that question there. Okay, let me look at summary 2018 now. Okay. Right, so I could just discuss this one a bit with you. Not go through it too much in detail, because it's my hope now that you could sit down and do this on your own, right? All you have to do is go back to all the notes and the rules that you learn, right? So that you need to practice in order so you could be able to perform it. And then in doing the midterm as well, you will be required to do some of this then in writing, in putting in some of the answers required that you will be doing online. You understand? So you have your Heaviside step function here. Use the definition of the Laplace to determine the Laplace of h at t minus 3. Right? So when they say use the definition of the Laplace, what you're doing is this here, you know. You're taking infinity and 0, right? E to the minus st by h at t minus 3. Right, so if you're doing this here now, remember the Heaviside at t minus 3 is defined to be 0 when is defined to be 0 less than 3, and it's defined to be 1 greater than 3. So if you break up this here between 0 and 3, right? You have e to the minus st. The heavy side is 0 plus infinity and 3. Right, and so therefore that'll be e to the minus s t over minus s, and you're taking the limit between infinity and 3. Because this part here will come out because it's 0 here. This part here is you're multiplying it by 1, so you'll get this here. So basically, you will get, remember here now, you take the limit as r approaches infinity, yeah? Right? So this top limit here becomes r. So that is, you have e to the minus sr over s, and then e to the minus 3s over s. So this part here will be 0 with the r in it, because once the numerator, once the power here is negative and it approaching infinity, that will approach 0. So this will be the answer here, e to the minus 3s over s, right? So that will be the answer here for here, which we already know, but you have to use the definition. So you have to go through the procedure here. See 6 marks. So by looking at the marks, it should be an indication that it's not like a two-step process. You have to go through the entire definition and explain everything. Right, so you want to sketch the regional convergence now. So you remember S in the denominator can't be 0. So it had to be greater or equal to 0. Sorry, greater than 0. Right, so you see it here, e to the minus 3s over s when the real s is greater than 0. So that is here. So you notice the imaginary axis here is a broken line or a dashed line, meaning it doesn't include 0 then. Okay, so the other part here now, consider the initial value problem, right? So the initial value problem here, y double prime plus 9yt is equal to cos 2t minus the heaviside t minus 4 pi cos 2t, right? And you have your initial conditions here all being 0, right? So you have here, by taking the Laplace transform of the differential equation and using partial fraction, show that ys is 1 minus e to the minus 4 pi s over 5 into s over s squared plus 4 minus s over s squared plus 9. And then you have to determine the solution yt. So what I like about this problem here is the two initial conditions are 0. Right, so when you're in the, when all the initial conditions are 0, it makes the problem a little easier to solve, to arrive at the answer, because those terms will just drop out automatically. So So on the left hand side here, you get s squared plus 9 and ys is your common factor. And then you're taking the Laplace transform of these terms here. So you'll have cos 2t minus ht minus 4 pi cos 2t minus 4 pi. Remember the 2t had to convert to t minus 4 pi, right? And when you use your trig identity, it's supposed to work out like this. So when you expand it out, cos 2t is the same as cos 2 into t minus 4 pi, which is like 2t minus 8 pi then. So the Laplace of 2t is s over s squared plus 4. The Laplace of the heavy side of t minus 4 pi is into cos 2t minus 4 pi is e to the minus 4 pi s over s squared plus 4. So your ys here will be s squared plus 4, s squared plus 9, right? This term here, when you multiply by 1, you'll get it back. And then when you multiply by e to the minus 4 pi s over s squared plus 4, you'll get the next term here. And then the partial fraction of s over s squared plus 4, two irreducible quadratic factors, so as plus b over s squared plus 4 plus cs plus d over s squared plus 9. And then you multiply throughout by s squared plus 4, s squared plus 9. And you will end up with this here, as plus b, s squared plus 9 plus cs plus d, s squared plus 4. And then you group it according to coefficients, a plus c s squared, b plus d s squared, sorry, a plus c s cubed, b plus d s squared, 9a plus 4cs, and 9b plus 4d. So a plus c is 0, b plus d is 0, 9a plus 4c is 1, and b plus 4d is 0. And when you solve here, the four equations here, you're supposed to get a is a fifth, b is 0, c is minus 1/5, and d is 0. So you could just factor out the 1/5. So you get 1 minus e to the minus 4 pi s over 5 into s over s squared plus 4 minus s over s squared plus 9. Because this will account for your minus 1/5 and this will account for your positive 1/5. You can pull out the 1/5 and you'll end up with 4 terms. S over s squared plus 4 minus s over s squared plus 9 minus e to the minus 4 pi s over s squared plus 4 plus e to the plus s e to the minus 4 pi s over s squared plus 9. So this will give us, when you take the inverse, cos 2t minus cos 3t minus the heavy side t minus 4 pi cos 2 into t minus 4 pi minus cos 3 into t minus 4 pi. So that takes care of number 2. Right? It was a little tedious to write all that there. That is why I went through the solution, the written solution. So this here is our transfer function once again. Right? Sorry, our differential equation, and ut is the input and yt is the output, and you want us to find the transfer function. Right? So ys over us will be 2s plus 1 over s squared plus 5s plus 6. And then you want to find your zeros and your poles. So you factorize the denominator, s plus 2 into s plus 3, and your numerator 2 into s plus a half. So we know that it will have a 0 at s equal minus a half, and two poles, two simple poles at s equal minus 2 and s equal minus 3. Right? Remember to put in your labels, x for pole and 0 for 0. And you could put a s plane if you wish, right? Consider the transfer function. GS is equal to 8 over s into s squared plus 2s plus 1. Use the initial value theorem to determine g as 0, the limit of t approaching 0 from the right gt. So you take SGS. So that will be what? SGS is s over s cubed plus 2s squared plus s. Look at here. 8s over, right? And if you take this here, the limit of s approaching infinity, what could have been done here is like, you could have do this like 8s right? So you could have do it like that. You multiply by the s on top. Okay, you'll have an extra s here when you multiply by s, and then you multiply by the s in the bottom, and then you divide by the highest power s, top and bottom, so that will be 8s divided by s cubed. The highest power s in the denominator. So that would be 1 minus plus 2 over s plus 1 over s squared. And this will be 8 over s squared over and this will approach 0. 8 over s squared will approach 0. And these two terms here at the bottom will approach 0. So you get 0 over 1, which is as the limit. S approaching infinity. You'll get 0 over 1, which is 0. And then the final value theorem. The same thing here again, right? You multiply by the s, right? When you multiply by the s this time, you cancel the s with this s here, so you get 8 over s squared plus 2s plus 1, right? And what should happen in here? This denominator here could be factored into s plus 1 squared, right? So which means your pole is minus 1. So if your pole is minus 1, the pole is on the left-hand side of the plane, or the complex plane. So therefore, the limit of s approaching 0 here, right, will be if you put S equals 0 here, you'll get 8 over 1. You see that there? So if I take the limit here of S approaching 0, let's go approach 0, so you'll get 8 over 1, which is 8. And we know that the pole lie on the left-hand plane of the left-hand side of the complex plane then. Minus 1 is on the left. It's like here. So once it lie on the left-hand plane, you know that the limit here will exist, right? And it means that the limit here, in this case here, is 8, right? So let me come out of this here now. Right, so this was quite a lot I was able to go through today, going through a lot of the past exams in the recent years for this course here. So your exam will have similar types of questions then. Now remember that on Friday, you must log in between 1 and 3. So from 1 o'clock when you log in and you start to do the exam, the midterm, the time will count down on you, right? And you'll have till 3 o'clock to complete and submit, right? So the system will grade you, right? So the questions are of the type that are described over the period of time I've been telling you about it. So a mixture of multiple choice and numeric questions up to the initial value problem. So nothing on the delta Dirac. So if you go into e-classroom, you'll see at the top of the course shell, you will see the course there, the exam there, the midterm, and you'll see the instructions, you'll see some information telling you about it and so on. So you could have a read and make sure you go through your practice and so on, and make sure you have yourself well prepared so that when the time comes around on Friday, you'll be able to do the exam and be successful, do well in it, right? So after today, I wouldn't see you again until after today is the midterm and then your final exam. I don't know, anybody know the exact day of the final exam, the day and time? All right, so this information would have to be forwarded to you soon, hopefully, because so what you're doing right now, you're preparing your right. So you're preparing for your final exam as well as your midterm. So make sure you continue working, right? I heard something about the 18th. I'm not sure as yet. So if you say you don't know, then it has to be confirmed. So keep checking, right? And make sure that you do the necessary preparations, right? So I'll take care. It was nice working with you, and I hope to see you sometime in the future, right? So we could end there for the day. Any questions?
Good morning, sir. Most likely the exam will be in the morning, although it will be hard to say, right? Most likely.
All right. So the morning of the 18th.
Yeah.
Right. So that hopefully will be like 9, right?
Okay. All right.
Yeah. No,
Okay, sir.
morning exams in UE does normally be 9.
Yeah. All right. No problem.
Right,
so thank you.
All right. We ain't confirm it as yet, yeah, but just saying if it's in the morning. Right?
Yeah, that's expected then. No problem.
Yeah. All right then. Anything else?
Not for me, sir. Thank you.
Okay. Okay, I'll see you all then. Take care. Bye.